Okay, welcome to the second class meeting of the spectrally correlated random processes. So as I announced it last time, we are going to cover the first page, which is J6, which I published it in 2004. It's around 20 years ago. This was the first paper I published after I became the professor. So all the other papers were all the other previously. Prior to this one was co-authored with my advisor. And in the United States, when you become a professor, assistant professor, the department asks you to be independent researcher. So at least you have to publish some papers without your former advisor, which means your thesis advisor. And the papers must be published in prestigious IEEE journals. So at that time, the IEEE transactions on information theory had a correspondence, which we believe has a slightly lower threshold than the regular paper. So even though the length was enough for full paper in other journals, I tried this one because I want to be a little bit safe. And I also was confident that the quality of this paper was good enough. Anyway, so let me start. The title of the paper is Joint Transmit and Receive Optimization in Additive Cyclostationary Noise. So as I told you last time, wise and stationary random process does not have spectral correlation. But one of the most interesting random processes are cyclostationary random processes, which exhibit spectral correlation. So this paper is about joint transmit and receive optimization in communication systems that exploits spectral correlation. So the situation is a little bit different from joint transmit and receive optimization in additive wise and stationary noise, especially additive white Gaussian noise, for example. So this is not that orthodox. And currently, even if you ask some other professors in communications area in the world, what about the difference between joint transmit and receive optimization in additive wise and stationary noise and additive cyclostationary noise, they would not know this result. So this paper is not well known because it's so technical in the sense that it's very theoretical. And even at that time when I published this paper, I didn't think this could be implemented in some way. However, as we will see almost at the end of this or in the middle of this semester, due to the OFDM system and its associated DFT spread OFDM, now we can do something similar, really implementable to this idea. Anyway, so let me draw first this part, joint transmit and receive optimization, because the difference between communications and signal processing is that we have a communication channel and we have a source here, information source, and here we have an information destination or a sink. And the task in communication system design is to put some, let me see. Put two systems here that connects source and channel, and that connects channel and sink so that we can transfer information through this channel reliably. And this part can be called as encoder and decoder, depending on what kind of view do you have. For example, if you view this system as a sub-problem in information theory, encoder and decoder, the terminologies would best describing this situation. So always remember that basically communication system design is to design a pair of two systems. One is here and the other is here. But in signal processing, our idea is a little bit different. Our idea is like this. Here is our signal source. And here is our destination or our observer. It can be anything. Let me just use almost the same terminology. Then what is the task in signal processing? Here you design this system. Called signal processor, so that from the output, which is observed by this system, you generate something useful here. It could be an estimate of some unknown parameter. It could be some best action you need to take, and some other things. Got it? So simply put, in communications, you design two systems. And there is some unknown system called channel. Of course, it's not completely unknown. It's known in some limited sense. In signal processing, you have a source and sink. And this is what you want to design. However, in many communications engineers, when they publish paper, it's very hard to distinguish it's a communications paper or signal processing paper. Why is it so? Let's consider some example. Suppose you are designing a receiver given a wireless communication standard, which means that you can't change this part. This part is given. For example, Wi-Fi. You want to design some access point in Wi-Fi system. Standard is fixed. So you are not completely newly designed encoder, but mostly you design this part. In that case, this entire thing can be viewed as this source in signal processing. In that case, you are designing decoder is similar to you are designing signal process. So in that sense, signal processing includes some communication system design. However, the most important difference in communication system is that in principle, you are to design a pair of systems in communications. So in the process of standardization of 5G, 6G, new Wi-Fi, they think about optimizing these two systems at the same time. So they choose some parameters for their LDPC code or some polar code to best utilize the channel so that they have reliable communication. Got it? Anyway, so this problem covered in the paper is a communication problem. We want to design these two systems at the same time under some limitation. And even though this journal is Transactions on Information Theory, actually this paper does not talk about any information theoretic metric. It handles mean squared error in the estimation of the data symbol. And some of very strict persons really hate this idea, and when they serve as a reviewer, sometimes they complain like this: "Hey, where is the information theoretic metric in this paper? Submit to other journals." And that is their point of view, there are tons of papers that do not talk about entropy, differential entropy, mutual information in their paper, but publish it in information theory. Information theory, in a narrow sense, is a Shannon information theory. However, in a wide sense, it's all about communications, signal processing, cryptography, and other things. So if somebody says, why this paper does not talk about any information theoretic measure but published in the transactions and information theory, I believe the person is very narrow-minded. Anyway, so let's see the block diagram first. And amazingly, the block diagram is simple. And as you see in the figure 1, we have a very special form of transmitted signal, or actually, this is the input to the channel. This is the input to the channel. And even the channel is very simple. The channel is modeled as an LTI system. Too simple. And it's not, of course, time varying. And we assume it's perfectly known to transmitter and receiver pair. So problem becomes easier and easier. And this is the received signal output from the channel. And this output is summation of two signals, which is the transmitted signals filtered version, this arrow. And here comes additive noise. And this noise is going to be modeled as a cyclostationary random process. And now let's see what is S and what is W. When we consider linear modulation, there are some classes of linear modulations called QAM or PAM or something. They have in common the channel input X in complex baseband proportional to the summation of data symbol and a single fixed pulse equally delayed as the time index of symbol increases. For example, let's say dn is either positive and negative 1, and p of t is a rectangular pulse with height 1 and duration t. Then what would be the sample path of this signal when this is modeled as a random variable? For example, if d0 is 1, then you have this one. d1 is negative 1 here. d2 is negative 1, then 1, 1, something like this. Got it? And it would be called, in this case, binary phase shift keying if you view this signal in the real passband like this. If you are not familiar with complex envelope notation, you are doomed actually. So this knowledge, which I say is prerequisite for this course and should have been taught in the previous classes, like some introductory graduate level communications and other things. So if you are not equipped with these terminologies, I ask you quickly drop this course and find other courses for you. Okay, so this is the real passband signal, and here x of t is a complex baseband signal, and this real passband signal could be said BPSK signal, BPSK modulated signal. Got it? So here you see I use the B of K. Sometimes I love D and B, but if I have if I would write this paper again, I should use D, but anyway, at that time I loved B. And here comes the direct delta function. And you may wonder why this is appearing here, but this is an old convention in communications society. So instead of directly describing, hey, this is our signal, they somehow define an LTI system called transmit filter. So this is transmit filter, and here comes direct delta modulated data sequence. And as you know from the shifting property, this output is simply sigma bk and st minus kt. So people could say this is the input signal. However, they somehow separated the so-called impulse modulated signal and a filter, just for mathematical convenience. You are not implementing this linear modulation signal in this way, never. However, this is very convenient in system design, as you will see. So the first objective, as you will see in the later part of the paper, is to design this S of t, which is the impulse response of the transmit filter. So this is called TX filter. Then what is this one? This one is RX filter. And you may wonder why we have this strange notation. And also, if I am rewriting this one again, probably I would love this notation, putting conjugation immediately after W, but it's okay. Yeah. Because as you will see, some people, when it becomes vector, sometimes they love something like this. Sometimes they love this notation and it's very confusing. But anyway, I would use this one and that one now. But at that time, I used somehow this notation. Anyway, one of the reasons why we have this one is that suppose the input to the receive filter is z of t, then what is the output of the filter, which is the convolution between w of negative t conjugate and z of t. And also one of the reviewer complained that, hey, this is very confusing. This means conjugation and this is convolution sum. Why don't I change this to something like this? I refused. But never do that, okay? Sometimes there are reviewers who really hate not to be a king or queen in the review process. Hey, I don't like that. You are not going to change? There are some reviewers, so always say that, okay, I'll change. But at that time, I was so young. So I kept this strange notation here, if I remember correctly. Or did I change the mind? Okay, I changed the mind. Okay. Here, as you see, convolution notation is changed. Okay, so I was not that young at that time. Anyway, so let me use O cross This is O cross or O times in LaTeX to denote the convolution integral. Now, what is the definition? Using the integration variable tau. Then, if I remember correctly, you have this. So it's nothing but correlation between the channel output and delayed conjugated version of the, just a second, something's not correct. Okay. Just a second. Yeah. So in tau domain, what you are going to do is that you have the z of tau and you delay w of tau by t. And you inner product. Because in complex, for example, inner product, you conjugate the first factor to compute the inner product. So this is something similar to this one, when W and Z are complex valued vectors. Got it? Anyway, that's why we have this strange notation of W of minus T conjugate here. And this is the impulse response of the RX filter. And now let me little bit summarize. Using two different terminologies. S of t is sometimes called transmit pulse, and W of t, pulse or waveform, and W of t is called receive pulse or receive waveform. Got it? So they are not equal to the impulse response of the TX and RX filters always. In this case, it's the same, but it's different. Got it? Anyway, so we are going to jointly design, transmit, and receive waveforms, receive pulses, to best utilize the channel and the additive cyclostationary noise in this paper. Then, let me ask you a question. So in this paper, we are assuming N of t, capital N of t, the additive noise is cyclostationary noise. Then do we already know the result of the joint transmit and receive optimization when N of t is Y-sense stationary noise? Do you know, or have you seen any result from your undergraduate and graduate textbooks? Amazingly, you cannot find. However, the problem was solved in in the middle of 1960s, late 1960s. I was not born. Even I was not born at that time. And in 1967, as you see, Transactions on Information Theory, the paper does not talk about any entropy and differential entropy and mutual information, but appeared as part 1 and part 2 paper. Optimum pulse amplitude modulation, transmitter and receiver design and bounds from information theory, but anyway. So this is assuming LTI channel and Y-sense stationary noise and solve the same problem with the problem tackled in this paper. So basically, this paper is extending a very, very old version of the classical problem. Now you understand why I try to publish this one in information theory transaction and why I was so sure about the acceptance of this paper, because it's so fundamental. Got it? It may not be interesting to many audiences, but usually the value of many papers are assessed based on whether it has a permanent record, it has a value as a permanent record or not. So as a permanent record, this paper is worth to be published, even though it would have been too late. For example, how many years difference do you see? Around 40 years, right? So the reference paper is published around 40 years ago, 40 years before than this paper. And interestingly, no one solved the problem. And if I have a chance to talk more about why I was motivated by researching this topic, it has very interesting story, but let me just focus on the paper first. Now, the title says optimization, right? So we covered up to this one and a little bit of that, but not yet. So optimization. Many engineering problems are first described verbally or mathematically in their domain, and then commonly transformed to optimization problems. And sometimes completely different area in engineering and science ends up with the same or almost the same or mathematically equivalent optimization problems. And probably you've seen many when you are taking convex optimization courses, right? The Stephen Boy's textbook starts with some strange face surface illumination problem, and it becomes some, for example, convex optimization problem like that. Anyway, so here we are going to formulate optimization problem given this setting of joint transmitter and receiver design. And let me review the structure of optimization problem. There are two classes of optimization problems. So whenever you think about an optimization problem, first thing is that whether it is a single criterion optimization problem or multi-criterion or multi-objective optimization problem. First thing is to divide the entire set of optimization problems into two parts. One is single objective optimization. The other is multi-objective optimization. And unfortunately, many introductory optimization courses even never mention the importance of multi-objective optimization. So when I was an undergraduate student, I vaguely knew there is something missing. And the hint was given actually in the class of introductory economics, because in almost at the last chapter of the textbook, the author of the book was talking about what? Pareto optimality and some other things, and game theory, something like that, where two different people, two different groups, multiple people, multiple groups wants to get something more from the society or, for example, stock market. My interest is different from my opponent's interest. If I gain more, he loses more, right? Then we both want to maximize each one's profit. That is all related to multi-objective optimization problem. However, fortunately, many engineering problems are, even though it is in principle multi-objective, are transformed or simplified to single objective optimization problem. And in this paper, we are dealing with a single objective optimization problem, where first you have minimization of an objective function of, for example, x. Then your minimization is over this vector x. Of course, it could not be limited to a vector of finite length. It could be a sequence. It could be a continuous function, continuous time function. It could be vector-valued continuous time function, everything. But just let me simply give you an idea. So we have FO, which is objective function. Sometimes people use 0, O and 0. So F0 is objective function of x. And you want to minimize. Of course, you can maximize, but in that case, you can put a negative sign. And here goes subject to. It's not such that. Subject to, sometimes abbreviated as S dot T dot, similar to such that, but it's not such that. X in some set. And this is called the constraint set. Constraint set of this single criterion optimization problem. So formulating an optimization problem is defining three things. First, what is to be optimized? What is to be found? Which variables are of interest? Second, what is your objective function? This is a scalar valued, usually real scalar valued. Got it? That is why we call it single objective. It's not a vector value. And we have some constraint. Sometimes it could be the entire set for x. However, in many cases, we have limitation. Got it? Now, what is the objective in this joint transmit and receive optimization? And here, you see Z of L, that is the sampled output of the receive filter at every capital T. And this problem is so simple. We are transmitting data symbol at every capital T. So we let the data symbol enter the channel every T second, and we take out some estimate of the L's B sub L, the estimate of B sub L, which is which is denoted as Z of L at every T. And what you want to do is very simple. We want to minimize the mean squared error between the L's data symbol and the L's estimate of it. So this is mean squared error between BL and ZL, if you want BK and ZK. And one better thing is that, of course, here we want to jointly design the pair of transmit receive waveforms. And interestingly, this problem does not have a constraint. We could design any S and W as far as signal power is limited. So actually, we have some limitation like S of t has finite energy of t or 1, or if you want anything. If I remember, no, I cannot remember. So let's see how I fixed. Oh, okay, so I cannot say that. Okay, because here, this B has some power spectrum which is not flat. So here is the constraint that Z of t, the input to the channel, time average, equals, let me see, t. Where it is? Anybody? Yeah, is it A? Yeah, AT, AT, AT. Some constant A, and which is used as a transmit power in this case. Got it? So this is the constraint. Why do we have such a constraint in additive noise channel? Because if we increase the transmit power, usually we can have better estimate. In the extreme, suppose that we have enormous transmit power. Equivalently, we have zero noise. In that case, we may, depending on the signal and channel, we may completely remove any error, which does not make sense. So usually, we put power constraint to the channel input, and which is the convention in communications and information theory. As you've seen in information theory already, Shannon also put the limit to the input power when he considered the capacity of the AWGN channel, right? Otherwise, capacity is infinite. So similarly, we put the power constraint here. And this is, of course, time average. And if you don't know what is time average of a random process, you are not prepared. Got it? I'm serious that you have to be studying kind of prerequisite materials intensively, otherwise you will not keep pace with other students. So now you have a clear idea what is to be solved in this problem. Then now let me ask you the problem again. What is the solution to this problem when the cyclostationary noise is replaced by Y-sense stationary noise? Anybody? What is your answer? That is answered, as I told you, the reference 1 of this paper, long ago. Of course, the reference paper 1 does not only talk about this problem, it talks about more, but here, the first paper published it, and the result was shocking, actually. Many people said, what? Because before, they didn't thought about this problem. They just took everything for granted. Hey, we have this transmit pulse and receive pulse, and this is communication system. They didn't thought about optimization problem. So it was so shocking at that time, which means there are following researchers by other people. So here comes Hansler's paper. And Hansler specifically talks about the mean squared error objective function and elaborates the results in the first paper. And Erickson also talks about the previous one by incrementally improving the result. He published one more thing, right? And here, you may say that, hey, professor, you said that the cyclostationary case is not solved for 40 years, but here you specify joint transmitter optimization for cyclostationary thing. Actually, in reference 5, N of t is still y-sense stationary. And B of k, as a discrete time random process, this is cyclostation. Got it? So in reference 5, the problem is modified in that direction, where data symbol sequence is y-sense cyclostationary. In my paper, interference or noise is modified to y-sense cyclostationary random process. Got it? So it's different. And then some 20 years later or 25 years later, there formed a group of researchers from AT&T Bell Labs. And they extended this result to multi-user cases. And if you know some history of digital communications, multi-user systems were gaining popularity in 1990s or middle of 1990s. And that is not the coincidence. And this is the extension of the previous work to multi-user cases. And they developed some interesting tools which were not used here. And that is in my paper called Vectorized Fourier transform. I didn't invent this idea. I just named it because they didn't name it, the previous researchers, around 10 years before at the publication of my work, right? And here, you need to have some understanding about the vectorized Fourier transform of a signal. Suppose you have a continuous time signal x of t that has Fourier transform pair capital X of f. For convenience, we use f for other purposes. So let me use xi, which is kind of number 3, left and right flipped, for the variable. Got it? So here, capital X of xi is defined as x of t e to the negative j 2 pi xi t d xi. Very hard to write, right? Anyway, so you may say that when you want to design some continuous time signal, for example, in the frequency domain, one of the choice is just to use the Fourier transform, right? However, it's just the conversion of a continuous parameter signal to another continuous parameter signal. The parameter now means frequency. Before it meant time. So no gain or no benefit is attained by this transformation. However, the vectorized Fourier transform is different. It's denoted by x underscore f. Here, underscore is used to emphasize this is a vector valued signal. Got it? So given f, you have a vector. Got it? And this vector valued signal has parameter f, which means a little bit different from that f you used in signal-gen systems. And let's see what it is. as figure 2 shows, you have the Fourier transform over deterministic signal x of t, now parameterized by xi. And what you do is that, given f, what you do is that you sample this signal, sample the Fourier transform at f, and uniformly with some pre-specified spacing. And here we are going to use the inverse of the symbol time for the sampling interval. So the channel input is conveying the symbol, one more symbol at every capital T. And this is used. Of course, vectorized Fourier transform can be defined with any sampling rate. But as you will see later, in this problem, sampling the Fourier transform with the inverse of the symbol time is very, very useful. Now, without limiting our bandwidth, actually, if we sample the Fourier transform, we will have a sequence that is not good. So we are, just for convenience, let's limit our interest to band-limited signals. For example, suppose our bandwidth of the signal is limited to plus minus 3 over 2t. Now, what happens? When we find the vectorized Fourier transform of the signal. So here, let's say this is f, and we sample at every 1 over t. What does that mean? We sample here, and we sample here, right? So if we have band-limited signal, then capital X of, let's say, some f0 equals what? Xi of f0, xi of x of f0, and f0, here we have to define which one would come first, and I subtract, I do not remember. Let me see. Yeah, I subtracted first. So 1 over t, I added 1 over t, something like this. The reason why we have only 3 elements in this vector valued signal is because the signal is limited to this one. And as you see, f also needs to be limited to this one. So you choose this one inside this area, plus and minus 1 over t. And that is actually this zone is called the first or zeroth Nyquist zone or Nyquist zone. Okay, it's called the Nyquist zone. Center Nyquist zone. Okay, and we have 2 more Nyquist zones here of the same length. So this width is 1 over t. Here, when we have overall bandwidth in passband 3 over t, right? Because this is complex spaceband signal. So passband from here to there, we have 3 over capital T bandwidth, right? It's divided by 1 over capital T, so we have 3. So this vector valued signal is of length 3 for every f in this Nyquist zone. And later you will see that this becomes very, very complicated when your bandwidth is not an odd multiple of 1 over t. Because depending on your offset f, sometimes this vector valued signal is of length 2, sometimes 3, something like that. That makes you very, very confusing when you use this one. But anyway, by the way, I was the first person who considered the band limiting this one arbitrarily. The 1990s paper for multi-user joint transmit and receive optimization papers, just because of this cumbersome variable length vector, they didn't want to handle. So they all assumed here, and these papers by AT&T Bell Lab guys and U of Washington, yeah, University of Massachusetts, they all assumed bandwidth equals passband. Passband bandwidth is odd multiple of 1 over t to make everything simple. But I didn't follow that. And that gave me some edge, which was not noticed by previous researchers when I extended this idea to a multi-user case. Got it? Anyway, I will also talk about multi-user case later, not in this paper, but anyway. So now let's see whether this vectorized Fourier transform contains the older information in the Fourier transform, ordinary Fourier transform. Let's see. So you have fingers, and it shifts by the offset f. And this offset ranges from negative 1 over 2t to positive 1 over 2t. And the finger spacing is 1 over t. Actually, it covers all the support of the signal. But difference is that now you have a vector valued signal at every f. And your offset f is limited. And that makes you utilize the powerful tool in your toolbox as an engineer. What is it? Linear algebra, vector algebra. Interestingly, this joint optimization problem becomes vector optimization at every offset f. And this is amazing because we are now very familiar with, most of you are very familiar with important results in linear algebra, like eigenvector corresponding to the largest eigenvalue of a Hermitian symmetric positive definite matrix. You know singular left singular vector and right singular vector and singular value decomposition of a rectangular matrix. You know what is Rayleigh's quotient. You know what to do with some vector matrix manipulation. So amazingly, this very continuous time-like optimization problem converts to vector optimization problem. The difficulty is that you have to perform vector optimization uncountably infinite times, because this offset f, even though it's limited to plus minus 1 over 2t, this interval consists of uncountably infinite number of value f. That is the problem, and that has been the problem when theoretical result by Berger in 1967 and other papers and all the other papers in the 1990s and my paper in this one was somewhat not appreciated much. They said that, hey, okay, I understand this is very fundamental. So what? We cannot design uncountably infinite times. Of course, we may approximate, but well, do your research, something like that. But as I told you in the beginning, in the era of OFDM, especially DFT spread OFDM, now we can use this. We can convert this result to do very interesting signal optimization. Got it? Anyway, the conversion of the signals to a vector valued signal takes very, very gradual development, which is given to you as a homework. So what you need to do is to follow all the lines in section 2 up to, where it is? Yeah, up to here. Got it? So this is homework. And you need to read, and of course, you cannot fully understand, but you have to do your best effort to understand every line here. Of course, I will explain some to you. But then come to the class next Monday. In the meantime, let me review the abstract and introduction with you today using the last 15 minutes. So in the abstract says that a joint optimization of transmitter and receiver is considered for strictly band-limited linear modulation in additive cyclostationary noise. And now you have little idea why I put this constraint. First, as you've seen in information theory, for example, AWGN channel capacity. If the channel is not band limited, how can you compute the capacity? Right? It could be infinite. Or you may have to use some limit operation. So band limiting is very natural in solving some fundamental problems in communications. Because usually, if we have twice the bandwidth, we have much better capacity or transmission rate or reliability or something. It's just that we have more money in our life. It's almost the same thing. We have larger bandwidth. We have better system. So without limiting, there is no optimization. Imagine some European trillionaire's son or daughter. Do you think they consider how much the Chupa Chups costs? No. They never optimize their spending, right? But we can't do that, right? So we limit the bandwidth, and it's natural. So this is okay. That is the first reason. Second is that this strict band limitation allows us to handle limited lengths in vectorized Fourier transform. As I told you, if the bandwidth is not limited, even though we sample the Fourier transform of the signal, we will have a sequence for every offset. And of course, there is a theory of linear algebra for sequences and infinite dimensional matrix. There is actually. You've never seen. You've always thought, okay, vector is of finite length, matrix has a finite number of rows and columns. Actually, that is not completely true. Even though we usually limit, and it's good approximation, but theoretically speaking, you may handle a vector matrix multiplication with infinite by infinite matrix and infinite length vector. Actually, you can do that. But anyway, And this, as I told you, constraint makes us to utilize ordinary linear algebra. We can utilize ordinary linear algebra tools in our toolbox. We are equipped with those tools from our freshman, right? By taking introductory linear algebra and some other courses. We can utilize them. And there are many linear modulations, but as I told you, our linear modulation is like more PAM or QAM type thing. Of course, you may wonder, hey, professor, this seems not completely general signal model. You are right. Many of you already have noticed. Is this too much limitation? Yes. Actually, the most general linear modulation looks like this. Okay? You may have freedom to choose nth transmit pulse. It could be different for every n, theoretically. However, the simplest one is what? Something like this. Single pulse shifted by the same amount. So you will see in some signal processing papers or some other things, there are linear modulation that may utilize different waveforms. Actually, direct sequence spread spectrum signal, like our GPS signal from the heaven, actually, it can be viewed as a linear modulation with time varying or completely different pulses for each symbol. Actually, it's not completely true because we are using deterministic pseudo-noise sequence. So it's periodic. But like we have million pulses generated differently. Up to million, then it repeats. Something like that. Got it? So actually we have some signal really having different transmit pulses for each symbol. But this paper and similar references assume the simplest signal model like PAM or QAM, where we use a single pulse delayed by the same amount, right? And I haven't yet still talked about this one. So why don't I do this? Okay. So let me defer the homework to next Wednesday, okay? Because it seems that I have to talk about the definition of cyclostationary random process next time on Monday. So you have 1 week, okay? 1 full week to study section 2. So here, of course, without some assumptions, limitations, problem is too wide. So we scoping down. The first thing is this one. Our cyclostationary noise or interference has, you will see, so-called cycle period. Cyclostationary random process has cycle period. And cycle period is assumed to be the same as the symbol period. Otherwise, problem becomes very, very complicated. It can be solvable, but very, very complicated. So this kind of assumes very simple situation, but it makes sense because in many cases, in cellular communication system, for example, this cell and adjacent cell or some not far away cell utilizing the same frequency band may use the same standard, which means that they have same symbol transmission rate and almost the same but distorted transmit pulses when received at a specific base station. So this is not that strange assumption. And this is called data-like interference. So this is a data-like interference. And as you will see on Monday, our signal is actually cyclostationary random process if we properly assume some probabilistic model. And similarly, our interference has same cycle period. It is not just happen to be, it's intentionally assumed to make the problem solvable. And as I told you, it makes sense in many important situations. And it talks about objective function of optimization. So let's minimize the mean squared error, right? And also, as I told you, Graph solved a similarly titled paper around 30 years ago with cyclostation something with joint. So the abstract must distinguish this work with that major reference. And that's why here goes. We assume data sequence is Y-sense stationary, but interference is Y-sense cyclostation. This is different from Graph's previous work where interference or noise is still Y-sense stationary, but the data of desired signal is Y-sense cyclostation. And actually, that extension of graph, I do not much agree because even if we encode our data sequence for error protection, usually the signal looks like Y-sense stationary random process, even white noise, as we've seen in information theory. As you've seen in information theory, the Gaussian code, which is the best code for AWGN channel, generates the code word symbol that looks like IID Gaussian random variables. So no correlation. Then no cyclostationarity. Got it? So I didn't like Graph's extension, even though mathematically it was very interesting. And of course, it was worth to be published as a permanent record, but it had limited application than this work of my 21 years ago. What else? So channel is assumed LTI, that is this part. And numerical results show that, of course, theoretically optimal is derived, and numerical results are provided, and this joint optimization leads to significant performance improvement in some cases, of course, not every time, in some cases, compared to receiver-only optimization. And that is natural, actually. Suppose you are doing joint optimization, and I'm doing only this part optimization. And we both do our best. Who will generate the better result if they have the same capability? Joint optimization always wins, right? So the result is actually obvious. But how much gain can he get is important. It's not like, okay, X is greater than Y. Usually, we are interested in how much is it. Is it just 10 to the negative trillion, right? So intentionally, I have found some example where significant gain can be attained. But of course, you may find many cases where minimal or negligible gain can only be attained. So that's the trick in publishing papers. Some people say, hey, here is a typical result. It's not typical. It's the best result. I really hated that. So I didn't say it's typical to have a significant gain. Okay? Sometimes it generates significant gain. Okay, anyway. Then there goes introduction. And I have around 2 minutes. So let me quickly talk about the importance of introduction. Now, we have significant revolution, the recordable revolution during last 5 years due to large language models. So non-US or British or some English-based culture student can now have much less headache in writing a paper in English. However, still, it is important that you know how to write a section, how to write a paragraph, how to write a sentence, and what kind of words you use in a sentence. That's still very important because it's not easy to teach everything to your LLM. Even though I asked Hyosun to do some side work to compile all, for example, my papers and ask the LLM to write his thesis, of course, his master's thesis in my English style using terminologies in this society. Are you progressing or not? Okay, great. So he will contribute to other students while he was about to graduate. So we will have some LLM trained well so that it generates some introduction and abstract with my style of writing. Anyway, so let me be quick. What is most important is that if you read 2 or 3 lines in the beginning and 2 or 3 lines in the end of a paragraph, you must know what should be written here. You must write in that way. Otherwise, your paragraph failed to communicate with the reader. Got it? So never, ever fail in that way. So read and you get the idea. Then it's a good paragraph. You read some lines and you get the idea. It's a good paragraph. Something like that. You must write that way. Got it? And also, another thing is that usually introduction is summarizing a literature, prior works of the authors or some other researchers. You don't need to be like a biblical scripters. A become father of B, become father of C. Never do that, okay? It's not just listing prior work. You are organizing the prior work so that your new result must be inevitably done. Got it? So it's like, hey, this is a destiny, something like that. You have to write your introduction in that way. I'm not saying that you lie, okay? I'm not saying you lie. You reorganize so that your work, your contribution shines much brighter. Got it? So that means actually, this is the most important one. When you read the introduction of other researchers' paper, okay, don't be fooled. They try to persuade you or brainwash you, or in this case, in this year's terminologies, how do you say that? 뭐라 그러죠? 뭐 있잖아요. 이렇게 brainwash 하는 거 뭐라 그래요, 요새? Gaswriting, right? Gaswriting you so that you become followers of your, not Instagram, but paper. Like, hey, this paper is some, so never be fooled, okay? So my way of reading the paper is like this. When some people say that, hey, have you read some blah, blah, blah researcher's paper? Not yet, okay, let me do that. And usually I print it and just read the title and think about what can be done under that title for a long time. And then I read the abstract and compare with what I imagined. And then I think about what could be done under that abstract and then read the abstract, introduction. Then I'm not brainwashed. Got it? Okay, that's all for today.